logistic regression, learned an equation, a curve with weights it tuned to the data. But here's a completely different idea. What if a model didn't learn an equation at all? What if it just remembered every example it had ever seen? And to make a prediction, simply asked, which of my neighbors does this look most like? That's k nearest neighbors, and it might be the most intuitive algorithm in all of machine learning. Let's switch to a picture with two features now, so every example is a point on a plane. Say we're sorting two kinds of flowers. The blue points are one species, the amber points are another. Each one is an example we've already seen and labeled. And this collection of labeled points is the model's entire memory. That's literally all it keeps. Now a new unlabeled flower arrives, the gray point in the middle. We don't know its species yet. With logistic regression, we'd plug it into an equation. But k nearest neighbors does something almost childishly simple instead. It just looks around. It measures the distance to every known point and picks the k closest ones, here the 5 nearest. Those 5 are its neighbors. The closer a point sits, the more it counts as similar. Distance is genuinely the only thing this model cares about. And notice, we didn't fit any curve and we didn't solve any equation. We just found who's nearby. Then it takes a vote. Among those 5 neighbors, we count up the classes, and whichever class is in, the majority wins. That becomes our prediction for the new point. 3 amber and 2 blue. Then we call it amber. And that's the entire algorithm. Find the nearest and let them vote. The one real choice you make is cow. How many neighbors get a say? Make k too small, like just one. And the boundary turns jagged, chasing every little bit of noise. Make k too large and it over smooths, blurring the real shape of the classes. The sweet spot is usually somewhere in the middle, and we often find it just by trying a few values. Now, something subtle but important. K nearest neighbors doesn't really train. There's no equation to fit. For this model, fitting just means storing the points. All the actual work happens later, at prediction time, when it measures all those distances. And because everything rides on distance, the scale of your features matters enormously. So we almost always standardize them first, putting every feature on the same footing. In Scikit-Learn, the pieces are a standard scaler to put the features on equal footing, k-neighbors classifier with our choice of k, fit to hand it the data, predict to take the vote, and accuracy score to grade it. It's a little longer than before, so once again, 2 pages, let's write it. Here's the whole program. Like last time, it's 2 short pages, and every single line is right here on screen. Don't worry about catching every detail on the first pass. We'll stop and walk through each piece. Page 1 sets up the data, and page 2 does the modeling. Let's begin. The imports, we pull in make blobs to generate some data. K-neighbors classifier, that's our model. Standard scaler for the feature scaling we just talked about. The usual train test split, and accuracy score to grade the result. Then we make the data. Make blobs is a handy little helper that spits out 2 nice round clusters for us. 200 points, 2 classes, with just enough spread that they overlap a bit near the edges, like real data does. We split it the same way as always, 80% to train, 20% to test, with a fixed random state. Nothing new here. That's page 1 finished. Let's turn to page 2. First thing on page 2, scaling. We fit a standard scaler on the training data, then transform both sets so every feature ends up with the same spread. Remember, nearest neighbors is all about distance. If one feature lived on a much bigger scale, it would quietly dominate every vote. Scaling fixes exactly that. Now the model itself. We create a KNeighbors classifier and tell it to use 5 neighbors, then we call fit. But remember, fitting here is basically just memorizing the training points. There's no heavy math happening yet. All the cleverness is saved for prediction time. Then we predict on the test set. For each test point, the model finds its 5 nearest training points and takes their majority vote. Accuracy score tells us how often it was right. Here, about 95%. Not bad at all for an algorithm this simple. And finally, we plot the data, coloring each point by its class, so we can actually see the two clusters the model is working with. Blue grouped on one side, amber on the other, exactly the data we generated up on page 1. And that's k nearest neighbors. No equation, no training in the usual sense, just distance and a vote. It's simple and surprisingly strong, though it does slow down as your data grows, since every prediction has to scan through all the points. Next time we'll meet a model that draws the single best dividing line with a clever twist: support vector machines.